Below the surface, of course, is the stagnant lid, in which the material from below can be outgassed. The volatiles can be dissolved in the melt. We include weathering of carbon dioxide if there's surface water present. Any oxygen that's released is instantly removed via weathering with the surface, we assume. We also include a dynamic model for the growth and retreat of the crust based on the thermodynamic and compositional evolution of the crust. Below that, of course, is the mantle, which convects between two conducting layers that we call thermal boundary layers. In this, we include the effects of water and melt. The crust is absorbed by the mantle by new surface pressing down on the crust, and that recycles carbon dioxide, water, and radiogenic species into the mantle. And you can see the species that we list there. And of course, below that is the core, which can convect if the thermodynamics are right, and that can drive a geodynamo. We do allow the presence of radioactive materials in the core, although a small amount. And of course, if the thermodynamics are right, the inner core can solidify, potentially quenching the entire geodynamo if the entire core solidifies. So I know that's a complicated model. Planets are hard, there's nothing we can do about it. But I'm happy to say that Rudy has been able to put this together. And here is some results. I think this is the first one-dimensional model of Venus that has successfully reproduced these observables. So the top panel there is the amount of water in the atmosphere. The middle panel is the magnetic moment, which is 0 on Venus. And the bottom panel is the amount of carbon dioxide, 92 bars. And the different colored curves here are the results of about 800 simulations that he performed, which were qualitatively different. In some cases, the core was still fully liquid. In other cases, it had completely solidified. Some cases have a lot of water in the mantle, others don't, etc. And you can see, hopefully, over here at the end, there are these little magenta lines that represent the 3 sigma uncertainties today. So it's a validated model. On the right panel, we see some other properties that aren't observed, but are now, we could consider them predictions. So what is the heat flow at the core mantle boundary? How much water is being outgassed from the interior right now, and how much water is escaping from the surface, or excuse me, from the atmosphere? And so, of course, these might be parameters that might be able to be detected by future spacecraft missions. For the purposes of this talk, though, I'd like to just point out that this is now a validated model of a planet in our solar system, and now the next step that Rudy's going to do after this is apply it to exoplanets and have this entire whole planet model to try and understand what happens to the water on these worlds as well. So TRAPPIST-1, of course, is the obvious example. All right, so moving on from the interior, we'll go up to the surface. And next we're going to talk about climates and ice coverage of Earth-like exoplanets. This is work that was led by an undergraduate, Caitlin Wilhelm, who has left academia for now, but she's left us with this great piece of work. And in particular, she was looking at this question of how does the ice coverage on an exoplanet vary due to host star orbital and rotational properties. To complete this work, she used an energy balance model, which is just a one-dimensional climate model in latitude, in which we divide the surface up into 3 components: ice, land, and sea, allow heat to move between the different components, and then look at what the final climate state is after 1 million years. And here's the result from her paper that also came out earlier this year, where the left axis is or the vertical axis, I should say, is the incident stellar radiation in units of the current amount on the Earth. And the obliquity is on the horizontal axis. The different colors represent the final states of the planets, at least in a qualitative sense. Dark blue are ice-free regions. They actually extend much higher up to much higher installations, but I'm just zooming in on the interesting part, which is where the purple and light blue are. So the purple are the polar caps, and you can see the Earth there at 23.5 degrees in one Earth installation. So we do reproduce the Earth. And then there's the white is the snowball states of total glaciation, where we might think the surface is inhabitable. And then there's this really interesting region over here, the ice belts, where the land at the equator is covered in ice as opposed to the poles. And what I find particularly intriguing about this, and I guess sorry it's being cut off there at the bottom, but when we compare this with models of planet formation, most of them predict that planets will tend to form with obliquities near 90 degrees. And that actually, from this results, then, and there's many other simulations. There were a total of 270,000 simulations in this paper. But what we find is that ice belts are going to be twice as likely as ice caps on planets around FGK stars. So we'll see if that pans out. Waiting for that EELT to be built to test this out. All right, so we're going to keep going in rapid fire here, so hope you're keeping up. Next, let's go to the planetary system and look at orbital dynamics and how that can affect the habitability of planets. In this case, it's going to be some work from me. I do occasionally get to do science. which is great. This is actually an old result though, so I can't be too excited about it. But you know, the question I was trying to ask with this work was how extreme can the orbital evolution of planets be? And I'm going to show you one example of a paper that I wrote in 2015, where we considered planets in mean motion resonances, but with some inclination. An Earth mass planet around a Sun-like star being perturbed by a Neptune mass planet that's orbit was 3 years, so 3-to-1 mean motion resonance. And we turned on an n-body model to look at what the dynamics were, and this is going to be an animation I'm going to show you, where the left panel is the top-down view, the right panel is the edge-on. So you can see there's some significant eccentricity and inclination here. The tick marks on the left panel represent the locations of the closest approach to the star. And I'm going to turn on gravity here, and you can watch with me how extreme orbital evolution can be. Maybe you've already seen this result, but I still think it's pretty fun and provocative to look at. So you can see that the eccentricity of this planet becomes quite large. The largest, the value I saw at about 800, or maybe it's 900,000 years, I think, is 0.99997. I have to count it on my hands because it's 5 nines. So a really large eccentricity, and you might think that this system can't possibly be stable, but I can assure you that it is. I've simulated it with three different codes and 3 different methods for 10 billion years, and this motion persists in a chaotic sense for that whole time. And so I think the answer is planetary orbits can be as extreme as you want them. Most cases aren't like this, but nonetheless, they can be this extreme. All right, moving on, let's talk about stellar properties. And I want to talk about the planets orbiting circumbinary planets, so thank you to Veselin Kostov for that great introduction to this earlier today. This is work led by David Graham at the University of Heidelberg. And so the question that we were interested in here was how does a circumbinary planet's orbit respond if the stellar binary is tidally evolving at the same time that it's evolving through natural stellar evolution, i.e. Magnetic braking and the contraction of the star as it approaches the main sequence. So what you should sort of have in mind here is that initially there's this eccentric binary star. We're going to consider 1/10 of a solar mass and 1/2 of a solar mass star, and the circumbinary planet is orbiting them. It turns out when you work through the physics of this that the binary star's orbit actually expands and becomes more eccentric due to this complicated dance between the tidal torque, the stellar evolution, and the magnetic braking. So the orbit actually expands and gets more circular, causing the circumbinary planet's orbit to react. But then once the stars reach the main sequence and their rotation rates synchronize with the orbital frequency, then tidal evolution proceeds as we might normally expect it, with the orbit circularizing and the orbit shrinking of the binary star. So here's a plot from his paper that came out last year, where the top panel is again the installation or the incident stellar radiation. You see it drop precipitously. That's because these are 2 low mass stars, and they take quite a while to reach the main sequence. The thickness that you see of those curves, it looks like thickness, but it's actually very high frequency oscillations that we saw earlier today due to the motion of the binary. And below that, you can see the 7 major axis and the eccentricity evolution over about 7 billion years. So this is evolution that can take place over a very long period of time, causing the orbits of these planets to change, and hence the climates and potentially the habitability of these planets. So we might say that the coupling of the stellar evolution and tides can drive these complicated long-term exo-Milankovitch cycles that could change the potential habitability of these worlds. All right, I got one more for you. Thanks for hanging in there. So next I want to talk about planetary dynamics. And there was some great discussion in the last couple of talks about, or at least the last one, I think, about Teegarden's star. Lion Gez, who is a graduate student at St. Andrews, they've been working on this problem of what happens to Teegarden's stars, planets, or obliquities. In particular, what they did is they looked at this case where initially we might think that there are these 2 planets that are potentially habitable. They're about the size of the Earth. But we think that their initial conditions were probably somewhat eccentric, and they could have again had obliquities somewhere near 90 degrees, represented by those arrows. This would mean that initially the tidal heating on these planets would be absolutely enormous, something like thousands of kilowatts per square meter. But the tides between the star and each individual planet tends to damp the eccentricity and the obliquity to 0, which would quench the tidal heating. But on the other hand, the planet-planet perturbations want to increase or sustain the eccentricity and the obliquity. What Lion found, though, is that after about 7 billion years of evolution, it turns out the inner planets, both planets become essentially circular, eccentricities of around 10 to the -5 or 10 to the -4. But interestingly enough, the inner planet, while its obliquity damps down to about 0 as we expect, the outer planet's obliquity can actually remain quite high as 45 degrees. And so that maintains a large amount of tidal heating, so that's why I changed the character of the inner planet to look like it's a habitable planet where the outer one is still like Io. Here are the results from their paper, where the top panel here shows you the final histograms of 1,000 simulations of T-Garden star system, looking at the final obliquity after about 7 billion years. As I said, the planet B's obliquity tends to be very low, but you can see C has a very wide range of possibilities, extending up to about 45 degrees. And then the bottom panel shows you the final heat flux, and as I said before, the planet B tends to have a much lower heat flux than planet C, and you can see I've marked where Io's approximate value is today. So this is really, I think this is a really fascinating result. I wouldn't expect to find a system where an inner planet would be Earth-like and an outer one would be Io-like, but yet that seems to be the case here. And also, just to address another issue that was brought up earlier, when these planets that maybe get to an obliquity of 45 degrees, that means as they go around their star, then the polar caps would experience a day-night cycle, which I think is interesting in terms of abiogenesis and things like that. All right, so we got through the first part for the most part. I took you on this quick tour around this map of planetary habitability, looking at these different aspects. One thing I didn't tell you, though, is that all of these results that I presented for you have all come from the same piece of software, a single executable that we call vPlanet, or the Virtual Planet Simulator. So this is our attempt to try and unite all of the different physical processes that are relevant for the habitability of a planet or moon in an arbitrary astrophysical setting. You can find this code on GitHub at the Virtual Planetary Labs GitHub site. We've done our best to follow all the software best practices. There's tons of documentation. Every single case up there is you can download the example and run it yourself. We have over 13,000 unit tests that we make sure the code is going to work. And you can use this. We have workshops every summer where we try and train people how to use this. It's obviously so much science out there. I hope that if you're interested, you'll reach out, and I'm happy to get you started on using vPlanet. All right, so that was the first part of the talk, primarily thinking about different processes that could be relevant for the habitability of different worlds. Let's go ahead and switch topics here and think about how we can actually calculate the probability of habitability on different worlds. So I want to introduce to you this new piece of software that Jessica Berkey has been developing called Alibi. It's a machine learning algorithm that basically allows for the rapid generation of Bayesian posteriors for different model parameters. So just at a really high level, what the code does is it uses Gaussian processes to derive a surrogate model that represents vPlanet, but can be evaluated in only 10 milliseconds, so it's very fast. And then the code uses other canned Markov chain Monte Carlo methods like MC or Dynasty, if you're familiar with these pieces of software that are very common in astronomy. It uses these codes to then build the posteriors with the surrogate model, and then, because the Gaussian processes give you a model for regions of high likelihood and high uncertainty, we can then intelligently select new points in the parameter space to run a forward model and then rederive the surrogate model to hopefully improve its accuracy in the regions of interest. And so through this iterative process of just constantly picking new points that we think are really important, the code can learn where the most likely parameter space is for the likelihood for the systems. So it's okay if you didn't follow all of that. Hopefully this plot will convince you that it works. This is a 5-parameter model for the XUV evolution of the TRAPPIST-1 system, where we've compared MC, one of these classic MCMC algorithms, with Alibi, this new code. We find that the posteriors differ by only a few percent, but crucially, Alibi required 1,000 times less computational resources. So whereas MC required a couple weeks on our supercomputer on 48 cores, Alibi can finish in your lunch break. So it's really remarkable. It's not quite a black box, so it does take a little bit of tweaking, but and nonetheless, I think that I'm convinced now of the power of machine learning, and I hope all of you can start thinking about it as well, because I think it's going to completely transform our field in the coming years. And of course, the hope is that this, I think, is more of a proof of concept than anything else. There's over 600 input parameters to vPlanet, so we need to extend to this high-dimensional problem, and I think maybe machine learning is the only way we're going to be able to get there. The last result I want to present with you is this work from Megan Gianluca, where she has tried to look into how do we actually model the TRAPPIST-1 planet's water loss, including the uncertainties now. And so what she has done is combined the posteriors for the TRAPPIST-1 star's XUV evolution with those of the planetary system. And then when you take those input parameters and you simulate the atmospheric escape, you can then start to model what is the uncertainty in the amount of water that's lost over time, which I think was another question that came up earlier today. The way that this is a different code we call vconverge that basically simulates this process in batches of 500 until the water content has converged. We don't use alibi here because there's actually no likelihood to match here. This is just about once you set the initial conditions and turn on atmospheric escape, it's deterministic. But you still want to understand what the uncertainties are. So it's sort of in picture form, this is what I'm talking about, where the figure on the left is the posteriors for the star. The one in the middle there is those for the planets, this incredible corner plot from Eric Egel et al. And then we add in the atmospheric escape model. And what we see is a plot that looks something like this, where the top panel here, I hope you can read it, the top panel is the water lost as a function of initial water content. And these are for the 4 planets that are potentially habitable, if you can include planet H. And that dashed line there is desiccation, meaning complete water loss. And the dots there represent individual simulations, and the line is an interpolation between them. And then the shaded regions represent these uncertainties derived by this process. And so you can see that they kind of flatten out because there's only so much time for the water to be lost. There's only so much that can be lost before the habitable zone arrives. And in our model, that truncates the loss of water. The bottom panel there shows you the amount of oxygen that's generated by this process. We include hydrodynamic drag and diffusion limited escape and things like that, if you're familiar with these processes. And so this is a fairly self-consistent model. And you probably can't see it here, but for planet E here, we generate something like 1,000 bars of oxygen in this case. So what we can interpret from these results is that if the habitable zone planets formed with somewhere around 3 to 5 Earth oceans of water, then that would suggest that they're probably totally desiccated based on our current understanding. More likely is that the planets actually have a lot of water. If you look at sort of assumptions that they have an Earth-like internal composition, they probably have somewhere around 100 or a few hundred Earth oceans worth of water right now. So we're on the right side of this diagram over here. And in that case, we can make statements like that the planets have lost 8, 5, 3.5, and 1 Earth oceans of water, plus or minus something less than 1 Earth ocean of water. Just a pretty tight constraint, which means you shouldn't believe it because this is a really simple model, right? This is no interior exchange of volatiles, just sort of a saran-wrapped planet. And we have saran wrap in Europe, but basically just an impermeable surface. So it's just the atmosphere. But I think, again, this is sort of a proof of concept of where we want to go towards understanding how these planets can evolve and how their habitability changes with time. So that's what I wanted to present with you today. I assume I've probably gone over. But anyway, this is my summary. It's basically just restating what I already said today, so I'll just stop here and take any of your questions. Thanks so much for your time.
It's time for some questions. Hold on a second.
Any thought about the primordial Earth-Moon system? The primordial initial Earth-Moon system, because during that time you have a collision between proton Earth and Moon.
So I mean, I've worked on that problem elsewhere. I didn't present it here, but yeah, I think that there's a lot of complications there, right? We don't know exactly what the initial orbit of the moon was, and also as it's evolved as its orbit has expanded, it's also probably crossed through some secular resonances with Jupiter and Venus that have kicked up its eccentricity over time. So the moon remains a really challenging object to understand. If you just take the simple tidal models and rewind them backwards, you get the obliquity going to 180 degrees and the eccentricity going to 1. And so it's a complicated problem that I haven't been able to address all of that here. I mean, there's also concerns about how tidal dissipation of the oceans has changed as the paleogeography has changed. So there's a lot in that question you've asked there, and I don't think I can address it fully in this context.
Rory, you mentioned that there's a lot to parameterize here. It's a lofty goal to try to put this into a single simulator, given what we know about the history of our solar system and the number of stochastic incidences in our solar system. The moon mentioned as being one of these. But a few years ago, people began to perform experiments trying to simulate magma ocean conditions. This is where you take the Earth and you melt it, because planets form hot, as was mentioned earlier. It was difficult to reach these experimental conditions. We're talking about 1,700 degrees C, 10,000 atmospheres. What they found is something remarkable. This is work at CNRS in France by Scaillet and Gaillard and others. That you degas an atmosphere very quickly after a planet has completed its formation. The amount of carbon and nitrogen that's found in the Earth's surface zone is predictable by this catastrophic degassing. So it seems to just go into the atmosphere and stay there so that the Cn abundance is more or less constant. Oxygen is different, hydrogen is lost, and so on. But C and N stay. And what's even more remarkable is that the same appears to be true for Venus. So you make the planet, it's melted, it degasses, atmophiles go into the atmosphere, and then since that time, its atmosphere crust interaction and modulated by solar activity. And the only way we could have gotten there is because of this advancement in experimental techniques. So that's why I was, if you could comment please on integrating such experimental results, in particular in light of the important result of the magma ocean degassing, interior versus exterior cycle. Thank you.
Yeah, sure. No, thank you for the comment. I didn't get to present it today, but vPlanet does include a full magma ocean model, but I didn't get to describe it today. So I definitely am thinking about those points, and certainly our model does outgas a lot of water and carbon dioxide. I mean, that is, as you say, a central and fundamental part of the magma ocean. But I think the broader point here is that there is a lot of modeling that goes into understanding what happens in planetary interiors, and incorporating that is difficult. And what we've done here is, in our magma ocean model, is basically we take, and really I need to give full credit to Laura Schaefer, whose model really, most is based on her work as well as Lindy Elkin-Stanton. But we've taken a lot of the work that they've compiled in terms of how, what the partitioning functions of these atmophiles are, and what happens with the redox chemistry in the mantle under various temperatures and pressures, and we just parameterize it or do interpolations of these tables that are published. At this point, I think that's really about the best we can do, because, as you say, this is a gigantic, high-dimensional problem. And right now, it's hard enough for us just to put the simple models together into this complex framework. My hope is that over the next 10 or 20 years, we'll be able to start refining our understanding of these things and kind of build off of this approach. vPlanet is a very modular code, so it's designed for plug and play with different assumptions. So I hope that I've built that into the code where we'll be able to make those adjustments as time moves on. But I just want to also say that I think that understanding the interiors of planets as a function of composition and mass is one of the grand challenges of the 21st century. I mean, it is so mind-bogglingly complicated. So please don't think that this is the end-all be-all of that. I think this is going to be a problem for much longer than I'm going to be alive. It's a real challenge. And I know I'm preaching to the choir with you, but for the rest of you, planetary interiors are really, really complicated. I'm sure you all knew that too, but I just want to make sure I say that again, because it's really hard to understand how we're going to do all that.
Well, no more questions. I think I'll ask one. But maybe it's similar to the previous one with a much more naive perspective. When you tell me that a model has 600 parameters and then you tell me it's validated by 3 points of agreement with Venus, I get a little nervous. And so in particular, the question is there a good understanding either within your code or within the community more generally of what features, what parameters are really the critical ones to get what things to work, and which parameters essentially make your best guess, but they don't matter that much for at least the current data that we have?
Well, it makes me nervous too, but at the same time, we have the observations we do, and we have the modeling and the physics that we've sort of worked out. So, right, I mean, that model of Venus, right, it's constrained by 3 parameters, and I can tell you that Rudy worked so hard for a year to try and figure out which ones were the most important parameters. So I don't want to say that graduate student years is the answer to your question, but in many ways, it just takes our brain power, and it's just going to take time to work through what are the most important parameters. In the Venus case, it turned out we started from something like 60 or so parameters, and he was able to show that it's about 12 parameters that really are the key drivers in the Venus model. So again, to sort of reiterate what I said to Steve is that, you know, we're kind of at this point. I mean, this is aspirational. This is a work in progress, but we're just trying to start from this point of just trying to put everything together, because these models do exist in these different scientific communities, and so just trying to bring them together and just see what works and what doesn't work is where we are. And I'm certainly looking forward to some missions to Venus to try and give us some more observational constraints to try and refine the model. Don't forget that there were multiple different qualitatively types of evolution of Venus that worked. Some that include like oscillating mantle temperatures and things like that. So even though it is validated in some sense, it's also not validated in another, and that it's still very ambiguous as to what the possible evolution of Venus is.
Okay, great. Thank you very much.
Yeah, my pleasure. Thank you, everyone.
Thank you for the talk.
Kirby, another question?
Oh, another question? No, I didn't see it. Okay. Last question.
This is a very big question. So what's so special about TRAPPIST-1? I mean, this is the third time we are hearing talking about TRAPPIST-1, and we hear that there are billions of planets, and a lot of people have found a lot of exoplanets. So can you comment on that?
Of course I could comment on that. Yeah, so the reason why TRAPPIST-1 is so interesting is because, well, there's many reasons, but I'll give you 2. One is that there are 3 planets that are Earth mass that are potentially in the habitable zone. So it's really interesting that we might be able to like understand some comparative planetology there, what's going on in this system. The second point is that their atmospheres are potentially observable with the James Webb Space Telescope this decade. Yeah, I see people giving me a CSE. You know, it's not obvious that it's going to happen, but at least hey, there it's possible. So there's several targets that could potentially be sites of life in this one system, and they're currently our best bet for observations of this decade for actually finding life on them. So.
Okay, thank you. I think we need to move on to the next talk. Next talk is my